Hello and welcome to the most exciting video series, Introduction to Convolutional Neural Networks. This is part one of the video series, and in this particular part we will be basically discussing the applications of convolutional neural networks, what a convolutional neural network, or in short CNN, can do. CNNs, convolutional neural networks, they are considered to be the game changers in artificial intelligence. Most of the tasks with convolutional neural networks, they are now been achieved with high accuracy that were considered close to impossible prior to the invention of CNNs. Several complex tasks, for example, automatic chess playing, automatic game playing, object detection, real-time object detection, which all these tasks they were having certain limitations in conventional computer vision techniques. But with the birth of convolutional neural networks, a lot of these tasks they just become achievable, and they are achieved now. Very stable software are available to actually do object detection. Very beautiful kind of AlphaGo players and chess players are now available that actually use the convolutional neural networks to actually achieve high accuracy. Actually, they call it the superhuman accuracy. They can actually beat the masters in that area. And these games that I will show you later on in this part, I mean, they are very complicated. The computer representation of those games in data structures, they are highly complicated. But yet these convolutional neural networks, they're able to actually achieve superhuman accuracy. So let's go first and see the object detection demo, YOLO version 3. I'm going to show you YOLO version 3, which is You Only Look Once, and this is version 3 of that. Version 4 is also out, but here is the demo of version 3 of that. This is a real-time object detector that actually detects objects in real time in videos. So let's see. This is the demo video, what it can do. Yeah, it's dog, person, that's a video. Everything is real time. Yeah. Awesome. Oh. By the way, it may make certain errors also. So look about errors if there are any. I will point out whenever I will see. Yeah, horse, person, dog. So that was an error. Dog. See, for example, the scale of different objects, scale, orientation, position in an image. That's all real time, detecting all real time. And see the diversity of the objects, the number of objects. That is also important. I mean, the huge number of objects. See the scale of this person. In the image. And it is also detecting the bag. The backpack. Wow. And the skits as well. Oh, it is detecting the bowels. Oh my god. See the scale of this person and the expression. It is detecting this as a dog, and that's an error. Oh, but now it converts it to a bird. Fine, finally it get it. That's an error. That's a camel, and it is detecting this as a horse. And this is also a camel, and it is detecting that as a horse, but that's an error. Fine. Oh, it's the only a foot is visible, and YOLO is detecting that as a person. See that? Only based on hand, it is detecting that as a person. See the scale of different persons. That's a bicycle being detected. Every person is being detected. This one is not, however. Oh, see that? Oh my god. Fish. Oh, it is detecting this as a sports ball. And that as a cell phone. That as a laptop, although it's a book. Backpack. Okay. I end this video here. Actually now, by the way, the great time to end. See, the only hand of a person is visible, and the object detector is able to associate this hand that this is a hand of a person. So this object belongs to a person. This is YOLO version 3. YOLO, I mean, it's a short form of saying you only look once. So if we just focus on the first letters, you only look once. If you just focus on the very first letters, that becomes YOLO. And that was practically the first big breakthrough, not the first breakthrough in convolutional neural networks, but that was the very fast and real-time object detector that was made available on several classes. I mean, the total number of categories, it was trained on ImageNet dataset, and the total number of categories of that dataset is about 22,000. I mean, these are the total number of types of objects that it was able to detect. And this algorithm has the basic object as a convolutional neural network. Although it has other details as well, and convolutional neural networks for object detection were also there before YOLO as well, like LeNet and other nets. But this YOLO was really real time. It was trained on a huge data set, and it was able to distinguish among thousands of classes, thousands of different categories of objects, and it was real time. It's very quickly compute the result, which was really a breakthrough. Although the faster variants of YOLO are available, this is version 3, version 4 is also available. There are faster RCNNs as well. But just to show you that this is now possible with conventional techniques in computer vision, earlier than convolutional neural networks, such an accuracy and such a speed was unimaginable. But with the birth of these convolutional neural networks, this kind of stuff is possible. This was one application. In the next clip I'm going to show you is the trailer from movie AlphaGo, and this is trailer from movie AlphaGo, and in this particular trailer, this is, by the way, this AlphaGo is from Google DeepMind team. Go is a game, and this AlphaGo is the artificial intelligence agent that actually plays this game Go, and it was able to beat the best Go player in the world, Seedle. And in this clip, they will actually show you the Seedle and stuff like that. In the next slide, I will also show you some of the basics of Go and how complicated this game is. But the point of story is, although this AlphaGo agent, it incorporates reinforcement learning as well, but one basic backbone of whole this framework is a convolutional neural network. So let's just go through this clip of this trailer.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lisa Dom.
A match like no other is about to get underway in South Korea.
They said all is to go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the Deep Mind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Well, look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong. Yeah, it's made a mistake.
It's got to be a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Yeah. So this AlphaGo basically is the player that actually plays the game Go, and this AlphaGo is basically a reinforcement learning agent. But what happens really is this agent actually not only deploys the reinforcement learning, but also the backbone of all this framework is convolutional neural network. So the most basic, fundamental component in all that framework is convolutional neural network. Although they have gone through a lot of improvements in reinforcement learning techniques as well. Particularly in AlphaZero, they deployed, for example, in place of convolutional neural network. Before AlphaZero, they were using InceptionNet. But in AlphaZero, which is improved version of AlphaGo, AlphaZero, actually they used, in place of InceptionNet, they use ResNet, residual net. And they have also improved the policy learning and stuff. For example, previously they were using Monte Carlo, but now they were using plain tree search and stuff. So they went through a lot of improvements in AlphaZero. So all these complicated kind of tasks, they become achievable or doable with the birth of convolutional neural networks as if not whole, as a component at least. So next we see, it is a common understanding that convolutional neural networks, they are for image data. Yes, they are for image data, but not just for image data. Now, the convolutional neural networks, they are also active in speech recognition. Although speech or audio signal is a 1D signal, it is not an image. Image normally is a 2D signal, and speech is a 1D signal. So for example, think about a speech signal as a 1D signal, and somewhere in here, we want a fixed length word to be detected. So in that, we may have a convolutional net that actually scans this audio signal like so in convolution form, and finally detect where that particular word lies in the signal. So it is, yes, it is for images, but it is for speech, and more precisely, it is for any structure that has some spatial or temporal kind of attributes. So for example, think about AlphaGo. AlphaGo is Go, the game Go. The Go game is basically in its full form, it's a 19 by 19 grid. So 19 by 19 grid, and you have two kind of pieces, black and white, or black player or white player, or black pieces or white pieces. And so you have to place different pieces in a way to cover more territory. There are certain rules for this particular game. But if you see the board position, each of this board, if you place black and white in different kind of these cells, you can think of as 19 by 19 binary numbers, and the total number of board positions are basically 2 raised to the power 19 into 19, which is 2 raised to the power 19 square, which basically is bigger than the number of atoms in the universe. And in Alpha 0, how they implement it is basically each configuration of the board is 19 by 19 by 17, where 8 features are for black pieces and 8 features are for white pieces, and they add one complete channel, 17th channel, for whose move is the next. So basically we have 19 by 19 by 17 structure. Now this is not an image, that's a basically three-dimensional matrix, and that structure actually is fed into a ConvNet, which is a ResNet, to compute salient features, and then the story goes in. So now if you think about AlphaGo or chess boards, they are not images. They are basically configurations or the representation of the states in structured form, and CNN actually take that structured form, which is not an image. So speech, the structured representation in form of matrices, videos. I mean, if you have several videos and you want to do a particular task and all the videos have same length, then you can go for convolutional neural network. And if, for example, the task is on videos where the length of the video also varies, then normally people deploy recurrent neural networks. But in these recurrent neural networks, each frame of the video, which itself is an image, is basically processed by a convolutional neural network. So what happened at the end of the day, whether you have applied a recurrent neural network to process videos, in the recurrent neural network, the basic building blocks are achieved by convolutional neural networks, and the recurrent neural network basically decides how many repetitions of the convolutional neural networks are there based on the length of the videos. So I mean, in its whole soul form, convolutional neural network is really, really important in its own, and it can be very, very beneficial in conjunction to recurrent neural network structures and in conjunction to reinforcement learning. So one way or the other, I mean, to achieve high quality kind of tasks, to solve complex kind of problems, one way or the other, nowadays, people have to go through convolutional neural networks as alone or as part of more complicated frameworks. And here is a map of structure of convolutional neural network. This is basically example of LeNet by Jan LeCun, the first practical convolutional neural network that the US also uses for their postal code, the number scannings. And basically, there are convolutional layers that I will explain in the next video. What is convolution? Then there are pooling layers, and these convolution layers and pooling layers, they have connections to the biological systems that I will explain when I'll explain the pooling, why pooling is there and why convolution is there. So these layers, convolution layers and connected to convolutional layer, pooling layer, they have biological connections, how the brain works basically, or at least how people pretend the brain is working through certain experiments. And once the structure, whether it's an image or any tensor structure, once it went through these layers, maybe multiple layers, then at the end they are flattened out and fed into an ordinary neural network, and that's it. I mean, yeah. But these filters, these convolutional filters, they basically are not fixed. They are not hand designed. The parameters inside these filters, they are basically learned. Yeah. So in the next video, in this particular video, I just motivate you about the applications and powers of convolutional neural networks as alone or as part of more complicated frameworks like recurrent neural networks and reinforcement learning like AlphaGo and chess playing and stuff like so. In the subsequent part of this video, we will see what is a convolution in detail, what is a convolution operation. And we will also implement convolution operation in Python, and we will see some of the more basics of convolution and stuff like so. And in the third part of this video, I will explain the terminology of convolutional neural network, like filters, paddings, strides, and all that stuff. So hope to see you in the next video, in the next part of this video series.